So I'm going to talk for 4 lectures on polymer kinetic theory, and the key here is introduction. So I'm not going to get into heavy stuff. So I hope you can follow me. I'm going to follow the following books. One is by Rubinstein and Colby. The book is on polymer physics. But I'll borrow from it to introduce you to some ideas from polymer statics, right? And then I'll follow the book by Bird, Curtis, Hasager, and Armstrong. This is called Dynamics of Polymeric Liquids. Volume 2 is on kinetic theory. Okay, so essentially these are the 2 books from which I'll take a lot of my material. Also, we had Professor Burkhard Dunweg from the Max Planck Institute for Polymer Physics, Polymer Research. He visited us a few years ago and gave a set of introductory lectures, and I thought they were great, and so I have borrowed from those as well. Okay, so I want to start by saying, and I think that's what as engineers we are exposed to, is continuum mechanics and the description of deformation and rheology from the continuum point of view. So typically, no matter what your fluid is, you need to satisfy the equation of continuity. And you need to, for an isothermal material, for simplicity, you need to satisfy the equation of momentum. G is the gravitational acceleration, P is the pressure, tau is the stress tensor, V is the velocity, and rho is the density. Okay, so no matter what your material is, you need to satisfy these conservation laws, and essentially, if you count the number of unknowns, you have 10 of them, right? Rho, the 3 components of velocity, and the 6 components of the stress tensor, because the stress tensor is symmetric most of the time. And so that's altogether 10. But you only have 4 equations. These are 3 for the 3 components of velocity, and 1 equation which is the scalar equation of continuity, right? So we're missing 6 equations altogether, and this is where really, because we have said nothing about the nature of the particular material we're talking about, that you need to augment these equations with what are called constitutive equations, right? And typically, you write these equations for the stress tensor tau. You need 6 equations, and when you've added these 6 equations that describe your particular body that you're interested in, you get a closed system of equations, right? Now, and you're all familiar with Newtonian fluids. For which we write where eta s is the solvent viscosity and gamma dot is the rate of strain tensor, right? And then this is how you close your system of equations. But of course, this is completely inadequate to describe non-Newtonian fluids, and non-Newtonian fluids broadly are classified into 2 kinds. One, and I'm talking about polymer solutions in particular. So you have the shear thinning aspect of polymer solutions, and there's also the elastic aspect of polymer solutions. And for simplicity, you can divide them into 2 broad classes. So you take care of the shear thinning aspect by the use of what are called generalized Newtonian fluids, which have the same form as a Newtonian fluid, but here the viscosity becomes a function of the strain rate, the magnitude of the strain rate, which could be is often defined like this. Okay, so by introducing a priori dependence of your viscosity on the shear rate, you can account for the shear thinning of your polymer solution. But of course, this doesn't account for any elastic effects. Now, if you want to account for elasticity, a very simple model is the so-called Maxwell model.
Sorry, can I interrupt you?
Yeah, absolutely.
The double dot is the trace of something.
Yeah, so this is a double dot product. So if you took the dot product of gamma dot with gamma dot and then took the trace of the result, that would be it. So it's a scalar. Yeah, sorry. Stop me if you need me to explain the notation. Right? Okay, so the Maxwell model is written in this form. Okay, where lambda 1 is a relaxation time, has units of time obviously, and eta naught is a polymer contribution to the viscosity. This is referred to as the differential form of the Maxwell model. You could also have an integral form, which, because this is a first order differential equation, you can integrate in a straightforward way, and you would get something like this. Okay, so you can see where the elasticity so this is the integral form. You can see how this accounts for elasticity, which is essentially saying that there's a memory in the fluid for past configurations, by saying that you see the stress depends on the strain rate at all past times, all the way to minus infinity. However, it remembers the recent past better because of this exponential decay than the distant past. The memory for the distant past decays, right? More generally, I mean, rather than use this form, people write integral equations that are like this. Okay, where g of t minus t prime is called a relaxation modulus. Sorry about that. The PDF annotator that I'm using has upgraded, so I'm not as familiar with this version as the earlier one, but I'll get familiar with this. No, this is the relaxation model. Yeah, sorry?
Not using one note.
No, not one note. This is called PDF annotator. It's I think they're all equivalent. Okay, so this is just to give you an example of constitutive models one writes in order to get a closure, and these are examples of what you do for polymer solutions. Now, of course, there are lots of shortcomings. I mean, obviously, the generalized Newtonian doesn't account for elasticity. The Maxwell model in its simplest form has a lot of shortcomings. Now, I won't spend a huge amount of time discussing where they fall short. Yeah, sorry.
If we take the two extremes, lambda tending to 0 and lambda tending to infinity,
Yeah.
is it like if lambda tending to 0, it is viscous response, but relaxation is instantaneous, and I didn't understand the other extreme, like lambda tends to infinity. How do we explain that?
So if you take this integral form and you can see lambda appears below t minus t prime, it sets the length scale over which it loses memory. So it forgets the past configuration on a time scale of lambda 1. So if lambda 1 is very large, it implies it remembers for longer and longer and longer, and a solid has perfect memory, right? As long as your deformation is elastic, it always goes back to its original configuration if you let it go. So that's the meaning of the range of lambda. Okay, so
Is it, I vaguely remember that there are spring dashboard models which you can draw for these.
yeah, so I'm going to come to that in a minute.
No,
So
I'm just thinking which one is this? Is the spring and dashboard in parallel or in series?
this is in series. Sorry, in that sense that you meant. Oh, yeah. I was going to come to spring models for polymers later on, but Yeah, this is in series. Yeah, so there are various versions of
I guess then lambda could be related to the strength of the spring or the dashpot in some sense, no?
So eta over lambda is the elastic modulus, right? Yeah.
But
So
that means the spring stiffness is going to 0 when lambda goes to 0.
no, the
When lambda goes to 0.
yeah, lambda goes to 0. Yeah. Okay.
Eta over lambda
Is the modulus.
Is a, yeah.
so if the
Right.
modulus if the lambda goes to infinity, then eta over lambda goes to 0.
Eta of lambda is the modulus.
See, we don't look at
Yeah.
time independently. We look
Oh yeah, so you have to think of it as a finite quantity. Yeah, okay, let's get into details then. I'll have a lot of ground to cover, and if we stop at this, we'll never, the whole lectures will, okay. So I'll welcome questions, but then I might say we'll talk about it later. Okay, if you don't mind. So as I was saying, so these equations have shortcomings, and people have proposed from a continuum point of view, how do we improve them? Right? There are lots of ways in which you can improve them remaining on a continuum level. But and of course mathematicians and engineers and physicists have come up with systematic rules for improvement of constitutive equations. So you accept certain axioms like material frame indifference or the second law of thermodynamics through the Clausius-Duhem inequality and so on, and these set constraints on the form of these phenomenological constitutive equations. So as long as you say my material depends on the following set of independent variables, you can come up with very general rules for what forms can these constitutive equations take. However, at the more sophisticated they are, the more material functions they have. These are called material functions, the viscosities, the relaxation times, the relaxation modulus and so on. And continuum theories do not give you the forms of these equations. We have seen here a very specific form for the relaxation modulus of a Maxwell model, but you can imagine if you have other models, you need specific forms for how the memory decays and so on. And that is where polymer kinetic theory is used. That is that we accept the molecular scale of your material as a reality, and then use simple models for the polymer, and then derive constitutive equations that will lead to explicit forms for these material functions. So then you are not left to postulating them on purely phenomenological grounds. Okay, so that's what I hope to do, rather than give a big introduction to kinetic theory in general. Show you how we can arrive at some of these simple continuum level constitutive equations from coarse-grained polymer models, and that tell you where how does one get explicit forms for these material functions. Okay. Now it turns out essentially at the when we try to approach rheology from a molecular point of view, we will find, and I will show you this subsequently, that it's the conformations of your polymer molecules on the molecular scale that decides the macroscopic rheology, right. So what shapes do these polymers take? How do segments on a polymer chain interact with other segments within the polymer chain? How do they interact with other segments on other polymer chains? And how does the solvent mediate the interactions of these segments with each other? Okay, and if we put all this physics in on a molecular scale, you can those are the elements that go to building your kinetic theory. And so at the very bottom of everything, or the foundation for everything, is understanding polymer conformations. So today's lecture will really have only introduction to how we begin to understand the conformation of polymer chains. Okay, and one of the most fundamental aspects of a polymer conformation is its flexibility. Okay, this is an essential aspect of polymer chains that we need to understand, and I am going to assume all of you know what polymers are and not spend any time on explaining what polymers are, but let us take maybe the very simplest polymer molecule, which is polyethylene, right, to understand this idea of flexibility. So what is polyethylene? You have these carbon bonds, and each of them is connected to 2 hydrogen bonds, and these carbon bonds go on and on and on and on. So, you can have from a few thousands to several million, right. That is the conformation of a polyethylene chain, and how the polyethylene chain is constructed is by using an ethane molecule for instance. So, if we took an ethane molecule, as you know, that is 2 carbons, each of which have 3 hydrogen atoms attached to them, right. So, how a polyethylene molecule is constructed is you remove 1 hydrogen atom from each of these carbons and add another of these ethane molecules. So, and that is how you build it. So, to understand this, it is convenient to look at this ethane molecule from above. So, let us say we line up the carbon atoms one on top of each other and look from above. So, I am going to say here is a carbon atom, and the one below it I will write right next to it. Okay. So, you have to imagine that the second carbon is vertically below this top carbon, okay. And the top carbon has got 3 hydrogens. Let us draw them like this, okay. So, these are the 3 hydrogens attached to the top carbon, and if we look at the bottom carbon and ask where are the hydrogen atoms connected to that, it turns out because these hydrogen molecules repel each other, the bottom one will arrange themselves like this. So, the dashed lines you can think of, I don't know what I did, that seems to have crashed. Okay, let us start again. Recovery. This has not happened before, so sorry about that. Yeah, I am going to do that, and let us hope. Okay. I haven't used this Surface Pro. I use a Mac, and for about a month now, and since yesterday afternoon I have been updating Windows ever since I arrived. It just goes on and on and on. I don't know why in 1 month it needed to update. So I have lost quite a bit here, haven't I? Okay, doesn't matter. I'll give you the notes. I have other notes for these. But I taught these same 4 lectures before, so I have the PDF. So we were looking at ethane, and so I was saying. Imagine one's next to the other, and we had aligned up the hydrogen atoms, and the dashed lines represent the hydrogens below, okay. And so, if you look at the projection from above, they are nicely aligned like a tetrahedron. There is a top tetrahedron with the 3 hydrogens, and there is a bottom tetrahedron with the hydrogens. So, now we are going to replace 1 hydrogen for each of these carbons with another carbon, right. So, let us assume the bottom one we have replaced with a carbon from another ethane molecule. So, now we need to replace the top one also with a carbon, and now you see we have these 3 possibilities, right. These 3 hydrogen molecules that could be replaced with a carbon bond. With a carbon molecule, and so let us for simplicity assume, or as the first example, assume that we have replaced this with a carbon atom, and of course each of these has got their hydrogen atom. So, in a sense this top carbon and the bottom carbon are aligned, okay, and this is called a trans configuration. We could have replaced either this hydrogen or this hydrogen, right, and that means if I denote this angle by phi, I could have either a phi taking on 120 degrees or a minus 120 degrees if the carbon had been used to replace the other hydrogens, right. It turns out all these 3 options are not the same energetically. So, if we were to draw the effective potential as a function of phi, the trans configuration has the lowest energy, and the gauche, and this is perfectly symmetric, this would be minus 120 and this would be plus 120. They are less energetically favorable. Now, suppose kBt was very small, okay, and then every carbon atom would be added in the trans position, okay, because that is the most energetically favorable. So, what you would get is a very long polymer chain with each, I mean it would obviously keep changing with the tetrahedron angle, but all the carbons would be aligned and you would get a very long rod. But it turns out this delta E, the energy barrier is roughly of order kBt when T is room temperature. Okay, that means if you are traveling along your carbon-carbon bonds, you can easily jump to a gauche configuration, and so you will very often see a gauche configuration. So, roughly if you worked out the probability, it turns out 1 in every 5 such carbon bonds are in the gauche configuration. So, you have very many configurations at room temperature where you are going from trans to gauche to trans to gauche and so on, and so it is not rod like, it is highly flexible at room temperature, and that is why you tend to see liquids rather than crystalline solids at room temperature, polymeric melts, and of course if you put them in solution there you get polymer solutions. So, and remember we had, let us say, n carbon atoms, and these are in hundreds of thousands, and at every position you have 3 options of where you can put your carbon atom. So, we have 3 to the power of n possibilities of where to put your next carbon atom, and so as you all know, the entropy is the proportional to the log of the number of configurations, right. So, we are talking about approximately n log 3 as the magnitude of the entropy, right, which means the entropy of a single molecule is large, and we can actually think in terms of a intramolecular entropy, that a single molecule can store entropy, and we will come to this later. So, this makes it clear that it is almost senseless to try to understand individual configurations, because there are so many of them that really it only makes sense to approach them from a statistical point of view. Okay, and if you looked at it at a large enough length scale, because they have every so many steps along the carbon backbone, it changes direction. That is exactly what a random walk is. So, physicists and mathematicians understand such configurations as random walks, and so the simplest configuration for a polymer chain for these reasons, one uses the idea of random walks. Okay, and so let us look at some examples of random walk models for a polymer chain, and one of the simplest of them is this so called freely jointed chain. Okay, so what is a freely jointed chain? I am going to assume that these monomers are connected by rods, right, and there are n of them, okay, starting from 1 and so on, I plus 1, and their positions relative to some origin are denoted by these position vectors r1, r2 and so on. So, your polymer or the freely jointed chain, its position in space can be represented by a set of position vectors r1, r2, r3 all the way to n. Okay. So, now I also want to talk about, so let us consider, just I will draw this again, let us say this is Ri and this is Ri plus 1. The bond vector is denoted by Li, that is the bond that connects Ri and Ri plus 1, and these have a fixed length. So, Li has its amplitude as L. Okay. Now, with the freely jointed chain, the assumption we make that is at every connection between one bond and another, there is no restriction on the angle that the bond can take. It can take any configuration in space, right, which means it is completely randomly oriented. So, if I took the mean, if I try to find the mean orientation of a bond, that would be 0, because it is isotropic and it could be, it is randomly distributed, right. And if I took the dot product of I with j, right, then this would clearly be L squared if I is equal to j, right. If I is equal to j, then I have just Li dot Li, and that, since each one has magnitude L, you would get L squared. On the other hand, it would be 0 if I is not equal to j, because one vector I is completely uncorrelated with the direction of j. It could be anything. So, I could in fact properly I would say, well, they are totally uncorrelated. So, the average of the product is the product of the averages, and each of them is 0, and so 0. A simple way of writing this would be using what is called the Kronecker delta. Okay. So, this would be delta ij, and this would be 0. This is if I equal to j and if I not equal to j, and the Kronecker delta is defined like this. It is 1 if I is equal to j and 0 if I is not equal to j. Okay. In terms of a matrix, it is just the identity matrix, right. So, when I is equal to j, which are all the diagonal elements, it is 1, otherwise it is 0. Okay. So, a property that we are really interested in for polymer chains, a large scale property, is the so called end to end vector. So, if I had my freely jointed chain which has got a configuration like this, I want to know what is this vector that connects the two ends. Okay. It is defined as Rn minus R1. Okay. Now, clearly if I were to take try to find the average value of the end to end vector, because all the bonds are completely uncorrelated, the end to end vector, yes, sorry. No. So, yeah, you are right. If this was a deterministic situation where you had two vectors and you took their dot product, they would be 0 if they were perpendicular. But here we are taking, so you should really understand, so maybe I rushed this a bit. From this, let us look at this first, right. Yeah, and I am assuming you know some probability theory. So, if you take the average value of these two quantities, if they are not correlated with each other, I and j, they are completely decoupled, then you can write it as a product of the averages, right. And each of them is 0 because you are asking what is the average orientation of this bond vector, and that can take any direction in space, and that is why it is 0, right. Exactly. Yeah, if you did the dot product inside the average, you are right, it would be 0 if they are orthogonal. But you are asking after you take the average and then you did the dot product, but the average already is 0. Okay. So, so we want to find this, and by the same kind of logic, because I hope it does not crash, it's frozen. I am blaming it on my Windows update. I wish I had done this earlier. It is completely frozen. Ah, okay. Have we survived? I'm sorry about this.
Next talk I'll get my surface through also. If this freezes, you can take that.
Yeah, or I can just go to the board. I don't know. I mean, this is supposed to replace a board, right? The advantage is you can save the PDF file, and in Monash they actually record all these lectures, whatever comes to the projector and it's through the mic. So but this is what I used to teach all the time. So help. Yeah, I don't know. Oh, there we go. Something has happened. Okay. Okay, so we want to find the average value, and that is 0, okay, because again of arbitrary orientations. However, the square is not 0. So if I found RE squared, and my pen width has, okay, that is not 0, and then that's something we are interested in. So if we want to calculate it, it would be okay. So firstly, let's see what this. You could either write it as Rn minus R1, or you could write Re as I'm going to change this. This is too small. As the sum from I going from 1 to n minus 1 of Li, right. These are the bond vectors. If I just add all the bond vectors together, it will give me the end to end vector. Now remember, there are n of these beads, but there are only n minus 1 bond vectors. So I sum them from 1 to n minus 1. So if I want to find Re squared, I could write this as sum over I Li, okay, from 1 to n minus 1, dotted with sum over j Lj from 1 to n minus 1, average, okay. And now I am going to just do some algebra. And so I will group the, I will bring the sums out. So there is 1 over I and 1 over j, and I will not write the bounds of these sums because it should be clear from the context, right. Li dotted with Lj, okay. And so now we saw that this is nothing but L squared times delta Ij, right. And so I could write this and remove the L squared, sum over Ij of the average of delta Ij, right. And so what I am doing is summing over all I and all j, and you remember delta Ij is the identity matrix, right. And so when I is not equal to j, they are all zeros. So the only ones that will contribute to the sum are the ones along the diagonal. And how many do we have along the diagonal? We have n minus 1 of them. So this sum will just be n minus 1. So you get L squared times n minus 1. So Re squared average is L squared times n minus 1. And we could define the end to end vector, the magnitude Re as the square root of Re squared, and that is L times n minus 1. And in fact, since n is very large, this is really sorry, n to half, and since n is very large, this is really n to the power of half. No chemist can tell you whether he has 1,000,001 or 1,000,002 monomers, right. So between n and n minus 1, there is really no difference when your n is very, very large. So, this is the famous random walk result that tells you that the size grows with the square root of the number of steps. Okay. Now, so obviously this is a useful result, but nowadays it might be easy to measure the end to end vector of a chain, but in the old days it certainly wasn't. It was very difficult to find what the end to end vector is experimentally. Now you could stain the two ends of a chain and watch it with a fluorescent microscope and get an idea. But rather than using this, people use something called the radius of gyration, okay, which measures the spread of the molecule about the center of mass. Okay. So, first we need to define what do we mean by the center of mass, and then define the radius of gyration. Okay. So, the center of mass is defined as 1 over n sum of I equal to 1 to n of Ri. Okay. Assuming that all the beads on your freely jointed chain, all the nodes have the same mass. Okay. And now, if I define the radius of gyration, it is done this way. What you do is you take the difference from each bead position from the center of mass. Oh, by the way, this is a vector, square it and then take the average. Okay. So, the ones that are close to the center of mass do not contribute a lot to the sum, but the ones that are further away contribute more to the sum, and this gives you another mean idea of the mean size of the chain. Now, it is actually not useful to have the center of mass here in the definition of the radius of gyration. There is an alternative definition completely in terms of the monomer coordinates themselves. And so, let us derive that, because that will prove to be useful for other things later on. So, I want you to consider this term. If I wrote Ri minus Rj the whole squared, okay, I could write this as Ri minus Rcm minus Rj minus Rcm the whole square, right. So, I haven't done anything, I have just added and subtracted the center of mass. Okay. And now, if I expand the square, then what will I get? I would write this as Ri minus Rcm the whole squared, right, minus 2 times Ri, oh sorry, these are all vectors, dotted with Rj minus Rcm plus Rj minus Rcm the whole squared. Okay. Now, if I were to take the average of this, right. So, minus 2 times the average, and I will take a sum over I and j. Okay. And let us take the sum in now. So, the first sum is over, there are only terms involving I, right. So, there is no j in that first sum, and you will recognize that the first sum is nothing but our definition of the radius of gyration, right. Because if you look here, the radius of gyration had Ri minus Rcm squared, and that is what the first term is. So, this is just n times Rg squared, right, the sum. So, the first sum, term, okay, is so sigma j times 1 sigma I of that term, which over I, that is just n times r g squared. Okay. And then if we take the second one, this would be 2 times sigma I average of r I minus r c m dotted with, because r I and r j are not correlated, right, I can take their averages separately, sigma j r j minus r c m plus, and you will see that if I take the sum for the last term, only j is there. So, it is sigma I of 1 and sigma j r j minus r c m the whole squared average, right. Now, this one, r average of r I is 0, average of r j is 0, because these randomly oriented, the bonds, and sorry, so this one was also, this is identical to r g squared, right, the definition. So, this is also n times r g squared. So, we have that, if I were to rewrite this, sum over I j of r I minus r j the whole squared average. Now, this sum of j from 1 to n is just n, right, because it is just 1 added n times, that is n squared. So, I will get 2 n squared r g squared. So, an alternative way of writing r g squared is 1 over 2 n squared sum over I j r I minus r j the whole squared. Okay. This is an alternative way of writing the radius of gyration. Now, but if you remember, R e, which was R n minus R 1, when we found R e squared, right, it was L squared times n minus 1, that is the distance from n to 1, right. Here I want to know what R I minus R j squared is. So, it is a freely jointed chain between I and j, and you want to know what is the connector vector between I and j, what is its average value. That is really just R e squared, not between n and 1, but between I and j, right. So, in other words, I could write R I minus R j the whole squared is nothing but L squared times I minus j, the modulus, depending on whichever is larger. Okay. So, in other words, I can now find R g squared, which was 1 over 2 n squared sum over I j of L squared times I minus j, because that sum is really R I minus R j the whole square. Okay. So, let us do this sum. So, we want to sum I minus j, I and j going over from 1 to n. Okay. So, the way we do this is to consider this matrix. So, let us say you have got a matrix, okay, and j counts the columns going like this. So, this will be 1, 2, 3 all the way to n, and I is the rows going 1, 2, 3 all the way, right, and we want to sum over I minus j. So, if you look at the diagonal, what is I minus j for the diagonal? 0. And how many terms are there? N terms, right. So, it is n terms, all of which are 0. Now if I look at the first term above the diagonal, right, what is I minus j for that? 1. How many terms are there? N minus 1. And how many such diagonals are there? 2. So this would be 2 times n minus 1 times 1, right, which is the value of I minus j. And then if I do it for the next one, there would be 2 such things, right, there will be n minus 2 of them and the value is 2. If I take the last one up there, how many of those are there? There are 2 of them, right, and what is its value? So I mean, and there is only one of those and the value is n minus 1, right. So let us write the sum then. Sum I j of I minus j can be written as n times 0 plus 2 times n minus 1 times 1 plus 2 times n minus 2 times 2 plus 3 times n minus 3 times 2 times n minus 3 times 3 and so on, going all the way to plus 2 times 1 times n minus 1. Okay. So now when n is so we will remove the 2 common, so a little more algebra. So I will remove so the first term does not contribute anything, so I will write this as 2 times, so 1 into n minus 1 plus 2 into n minus 2 plus 3 into n minus 3 plus so on. Okay. When n is very large, we can substitute a sum with an integral. Okay. So we can write this as 2 times, okay, integral 0 to n dx of x times n minus x. Okay, that is what the index is, and if you did that, this is straightforward, right. 2 times nx squared over 2 minus x cubed over 3 going from 0 to n. So that is 2 times n cubed over 2 minus n cubed over 3. Am I doing something wrong? Is correct so far? Yeah. Okay. So there was a prefactor, right, for our Rg squared. It was 1 over 2 n squared. So and so this now has a common 2n cubed, right, 1 over 2, so that is 3 over 6 minus 2 over 6, that is 1/6, right. So that is 1/3 n square n cubed. Yeah. So and so this is times 1 over 3 n cubed. So you oh, and there was an L squared. I am missing an L squared. So I just want to make sure I wasn't missing this L squared up here as well. I had it in there. Okay, sorry. So, ouch. There's a simple way. Okay. So we have now got this is L squared over 6 times n, and if I define Rg as square root of this Rg squared, you see it is L over root 6 times square root of n. So we found a very important aspect of polymer chain statistics and in polymer physics in general. Firstly is that the large scale properties, whether it's Rg or Re, they are scaling the same way with the degree of polymerization, and n is the degree of polymerization, right. And the local structure is only entering through the length scale L, which is the bond length or the monomer size, right. So in fact, we saw Re scaled the same way. So if you remember, Re was just L times square root of n, and if you take the ratio Re over Rg, it's just 1 over square root of 6. So this is independent of the degree of polymerization, independent of the local chemistry which comes in through the monomer size, right. So physicists like to call this a universal amplitude ratio. It's universal because it doesn't depend on anything, it's just the polymer property, large scale property ratio. Okay, and we'll, I don't know if I'll have time, but we might see other such universal ratios when you deal with polymer properties. Okay, so that gives you an idea of what and what was I going to do. Okay, now let's make the random walk model a little more general, right. So the freely jointed chain allowed you to take any configuration from one bond to the next. But we know when we saw how in a polyethylene, for instance, the carbon-carbon bonds were directed, there was a tetrahedral angle that it kept following, right. So one, regardless of whether it's trans or gauche or so on, we can make a simple model that accounts for this rigidity in the direction with the simplest next model, which is called a freely rotating chain. Okay, and what is a freely rotating chain? Okay, let's draw it here. So imagine this is one bond, okay, and we'll say this is Ri and this is Ri plus 1. So this is Li, the bond vector. Then the next one we are saying can take any direction here. So this will be Ri plus 2, but it's free to rotate with this angle theta. Okay, that's not fixed, and I mean that is fixed, but once you fix theta, it can rotate about this fixed angle. So it could be anywhere here. The next bond, for instance, that's supposed to be a dashed line. So that's the continuation of where the previous bond is, but this one could be an angle theta from there. So it can rotate about an angle theta and so on, and so that is the general configuration of a freely rotating chain. And so we want to study the properties of this freely rotating chain. So for instance, okay, let's draw this again and do some lay some notation here. So I've got Li, right, and let's say this is Li plus 1, okay, and I will denote n hat I as the unit vector in this direction, okay, and n hat I plus 1 in the unit vector along Li plus 1. So in other words, n hat I is Li divided by L, okay, and I am saying this angle is theta, okay. So if I took a projection of this on this in the direction of the previous bond, then since this length is L, this would be L cos theta, right, and it's in the direction of Li because I am taking the projection in the direction of Li. So it will be multiplied by the unit vector Ni, that is this projected size. Okay. So, now Li plus 1, right, is free to rotate any direction as long as it maintains that angle theta. So, we could imagine we will call this vector delta I, okay, and then I could write Li plus 1 as L cos theta times Ni plus delta I, right. It is this vector is Li plus 1 and this is this one, this vector, and this is delta I. Now, the thing about delta I is it is a random vector, because it can take any direction. Only L cos theta is in the direction Ni. Okay. Now, one thing we can do is, because I have L times Ni here, that is nothing but Li, right, L times Ni, because Ni is in the direction of Li, and times L, that is Li cos theta plus delta I, where delta I can take a random direction. And now, we want to find the end to end vector of a freely jointed chain. Now, I am not going to do all the algebra, because it would take a lot of time and it is very tedious, but I will show, and because it will introduce some other ideas to us that are useful, I will show you some of the basic working involved with finding the end to end vector for a freely rotating chain. So, let us consider this quantity Li plus k dotted with Li, okay. That is the Li and something that is k bonds away, Li plus k. Okay. So, and use this thing that I have just introduced about how I could write Li plus k in terms of this random vector delta I. Okay. So, this would be I could write as average of Li plus k minus 1 cos theta plus delta I dotted with Li, right. Just because I am interested in Li plus k, I take the previous vector, that would be this one, and add the perpendicular direction delta I, right. And I could then expand Li plus k minus 1 in the same way, and I would write this as Li plus k minus 2 cos theta plus oh, I should this is not delta I, it is delta I plus k minus 1. It is so let me write that. Okay, and then so this would be delta I plus k minus 2 times cos theta, okay. That is that plus delta I plus k minus 1 the whole times dot delta I. I just using this idea about how I can expand Li plus 1, right. So, let us take that in. So, this would be average of Li plus k minus 2 cos squared theta plus delta I plus k minus 2 cos theta plus delta I plus k minus 1 the whole times dot Li average. Okay. Right. Now, you can imagine I can keep okay, let us do the average here for the timing. Let us take the average in and you will see something immediately is, so this is average of Li plus k minus 2 cos squared theta dotted with Li plus, now the delta I plus k minus 2 is completely uncorrelated with Li, because delta I is a random variable, all the deltas are random, and so the average then has to be 0, okay, and similarly the next one is also 0. So always the deltas averages go to 0, you are only left with this, and this you can keep going back, you know, doing k minus 3, k minus 4, and you can go all the way till you are back at Li, and that would just be Li dot Li, right. And you see that the sum is always k minus 2 and the exponent of cos is 2. So k minus 2 plus 2 gives you k. So if we went all the way down, you would get Li dot Li times cos to the power of k theta average, okay, and this and cos you remove from the average, so it is just L squared cos to the power of k theta, okay. And since cos theta is less than 1, you very quickly, when k becomes large, get a very, very small number. In fact, it decays exponentially, and you can show that by saying writing this as cos to the power of k theta is the exponential of the log of cos to the power of k theta. So you are just taking an exponential and a log, and so this is exponential of k log cos theta, okay. And we are going to introduce a notation here, and I am going to say SP is minus 1 over log cos theta. Yeah?
We are assuming theta to be same for all the monomers. Is it because we are considering only single type of the monomer, or if you consider different types of monomers?
Of course, yeah.
Theta will change, right?
Yeah, absolutely. If your polymer chemistry is complicated, yeah. So what I am trying to do, and I should give you that right away, is that we are trying to simplify a complicated chemistry to a very simple coarse grained representation, because it will turn out later on that rheology does not depend so much on the details of the chemistry of the polymer chain. As long as we can capture some basic large scale properties, that your polymer can be oriented, that it can be stretched, and it has many degrees of freedom and so on, that is enough as far as rheology is concerned. So we are trying to work out what are some simple models with which we can work with. In fact, we will throw away even a lot of this detail soon, okay. So yeah,
How about the branched polymer?
a branched polymer.
Linear chain. If we have branched polymer, then will this analysis be applicable?
No, certainly not. So if you are familiar with physics, they talk about something called a universality class, okay. So everything that belongs to a certain universality class behaves in a certain way, and you look for what is called the minimal model of the universality class, which will capture things like critical exponents, large scale properties and so on. So certainly this is only for linear chains, and we are trying to work at what is the minimal model with which I can get results for linear chains. For a branch polymer, I would have to come up with a different model because it belongs to a different universality class, okay. Yeah, sure. So if I define this way, then I could write cos to the power of k theta as e to the power of minus k over sp, right, and sp is called the number of segments in a persistence length. So you can see as k becomes large compared to sp, this exponential decays rapidly, right, and that is why this cos to the power of k theta decays rapidly. In fact, this will prove later for some things I want to talk about later on. We could define Lp as sp times L, okay, which Lp is called the persistence length, and then you can see cos to the power of k theta is e to the power of minus kl over Lp. So L is a bond length, kl is that many bond lengths, right, k times L distance. When that is large compared to the persistence length Lp, your cosine function goes rapidly to 0. Okay. So, so that is what we saw here was Li plus, so did I write what Li plus, yeah, is L squared, right. So, we have derived that Li plus k dotted with Li was L squared cos to the power of k theta. Now, what do we want to find? We want to find the end to end vector of a freely rotating chain. So, we know that Re, and this is true in general, I comma j average of Li dotted with Lj, right. We yeah.
In the first model, theta is random. When we say random walk model.
Correct.
But here, this is a more constrained model. Or
It is. So I'll actually show you when we'll get the two limits. We'll get back the freely jointed chain by considering this. You're right. Here we're keeping theta fixed, and so yes, exactly. Yeah, we are saying it only has to have an angle of theta when you go from one bond to the next, but where it is located spatially, that's arbitrary. Okay. Okay, so from our argument that we have just made, you can see that Re, sorry, this is Re squared. From the fact that I had Li plus k and I, here I have got I and j, and so j is I minus j away from I, right. So, I can write this as L squared sigma I j cos to the power of modulus I minus j theta. Okay. And this is where I am just going to wave my hands because the algebra will take us a lot of time, but what you have to do is do the same thing like I said about the diagonal, the off diagonal and so on, and then calculate the I minus j for each of these, and if you put it in there and consider n becoming a very large quantity, you can finally show, and I will just write the final result now, that for a free, and if you want to know the details of the algebra, just go to one of the sources that I have pointed out and you will find the detail. So, R E and this is average. Sorry, I might have been loose about this here as well. It will turn out to be L squared n 1 plus cos theta over 1 minus cos theta. Okay. So, for a freely rotating chain. So, what do you see at the end of the day? What has happened is that you get a correction term to the end to end vector of a freely jointed chain, right. And so, you can imagine as theta becomes smaller and smaller, okay, then it approaches 1. And so, Re squared becomes a very large quantity for a freely rotating chain. So, if you make it stiffer and stiffer, and that is it cannot have a lot of freedom in this angle that it can take, it becomes a longer and longer end to end vector. So, if I had, on the other hand, like you said, if the average of cos theta was 0, it is a random chain, then this term would drop out and you are back to the freely jointed chain L squared n. So, that actually, and so what this term is called, this for stiff chains, you call this correction term C infinity, okay, and the infinity comes from the fact that this derivation requires you to consider very large n, okay. So, that in for the freely rotating chain, C infinity is 1 plus cos theta over 1 minus cos theta, and you can think of C infinity also as Re squared for a stiff chain divided by Re squared for a flexible chain where the flexible is completely flexible, and that's Ln squared, right? And then you would get which for a freely rotating chain has this value, but this definition is general, and so you can apply it to different polymer molecules, right, to get an idea of how stiff it is. And it turns out that for polyethylene it's roughly 6.7 or something like that. Okay, so it tells you need to have about 7 bonds before you get a decay, and you go further. What are we doing for time? Yeah, well, another 10 minutes probably. Yeah, I probably won't need 15 minutes. I've probably been going faster than I thought. Okay, so in general you write, and we have done that, Re squared is N L squared times C infinity. Okay. Now I want to actually look at something even simpler, and that is the following. It's called Kuhn chain. Now we saw that if you travel along the backbone of the carbon chain, if you traveled a sufficient distance, then you lose all correlations because of how quickly it decays. So let's imagine now, and we've also seen that the local structure of the chain only appears through this L term, and here through cos theta and C infinity, right. Now imagine I have a very long chain and I lump monomers into super monomers, right. And for instance here, if I imagine I have a super monomer that's longer than the persistence length, right. The minute I do that, the super monomers are completely uncorrelated with each other, right, because they are longer than the persistence length. So if I looked at the correlation of one super monomer with another super monomer, you are already at a length scale greater than the persistence length, so that should behave like a freely jointed chain. So that helps us define something called a Kuhn chain, which has nk Kuhn steps, and this is a freely jointed chain, okay, and where each step has a length of bk. So because it's a freely jointed chain, we can write right away that Re squared is nk bk squared, right, just like we had L squared times n. This Kuhn chain, which has super monomers that are of length bk, and there are nk of them, we would write Re squared like this. Now why are we doing this? Because we are interested in large scale properties. As long as I represent my polymer with a model that can capture the large scale properties, I am not so worried about the local details, and that is why I am coming up with another model, and here I call it a Kuhn chain, which will have the same Re squared, and we could say the contour length, here it is nk times bk, right. This is the length of my chain. If I stretch it out, there are bk of them, and each one has bk length, and there are nk of them. So the stretched out length would be nk bk. I want to say, well, my chain, this simple model, I want it to represent a regular polymer, but I want it to be a freely jointed chain, okay. So for instance, if we compared it with a freely rotating chain, right, what do we know about a freely rotating chain? I would say Re squared is L squared n times C infinity. And how do I find the length of my freely rotating chain? Let us say okay, so I have got this vertical line, and I line up my freely rotating chain, right. These are the bonds like this, and this is theta, because that is the angle between the bond and the previous bond direction. So each of these angles then is theta over 2, right. So if this has a length L, then this projected length is L cos theta over 2, right. So each of these lengths is L cos theta over 2, and how many of them do I have? I have n of them. So L would be n times L cos theta over 2. That is the length of my freely rotating chain. Okay. So if I want that to be the same as my Kuhn model, so notice that if I found the ratio Re squared over L, that would be Bk, right, from here. And so what is Re squared over L for a freely rotating chain? That is L squared n C infinity divided by n L cos theta over 2, right. So the n cancels and I would get that Bk is L times C infinity divided by cos theta over 2. So if I had the properties for my underlying polymer chain, what is its C infinity value, what is the theta that decides its stiffness, I could calculate the Bk of a Kuhn model. And similarly, you will notice from the definition that if I take L squared, so let us go back here, sorry. L squared over Re squared, what is that? This would be Nk squared Bk squared divided by Nk Bk squared, and that would be Nk, right. So then I can find Nk from L squared over Re squared. For a freely rotating chain, I have got n squared L squared cos squared theta over 2 divided by Re squared was L squared n C infinity. Okay. So the L squared and L squared would cancel, and this would give me n times cos squared theta over 2 by C infinity. So for any freely rotating chain, I can find an equivalent Kuhn model. Okay. I think we can stop here. It's a good time. We will continue next time. Okay. Thank you. Yeah, now we can use the remaining time to ask questions. Sorry. Yeah.
So, the difference between the freely rotating chain and the freely jointed chain,
Yes.
was that one scaled as square root of L and the other scaled as N, is that right?
No, 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 no. Both.
I missed that.
I am missing an n.
I don't know if it's scrolled up.
Okay.
Maybe I didn't follow.
Re squared. You are looking at the Re squared for both. Yeah, yeah. Both are n.
Both are N.
Yeah.
Earlier it was Re that you were found. Right.
Ah.
Re was square root of L.
Yes. Correct. 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 That's the random walk square root of n. Yeah.
To the point where we define some kind of amplitude ratio as 1 over root 6.
Yeah.
So that's like
Yeah.
we had an expression like 1 by root 6 n times L cube.
Yes, that is Rg. L and to the 1 by root 6 would be L times square root of n. Yeah, right? Yeah.
And we had a move from summation of n minus 1 summation to integration assuming and we have very large n.
Yeah.
So continuing with the same in the same line, why don't we drop the 1 by root 6 factor as well, which comes out to be 0.4, saying that n is very large.
Yes, as far, so when we only want to consider radius of gyration, right, then what we are interested in is it's going as square root of n. We don't care about the prefactor. That is the idea of scaling laws. You only want to know how does it change with the degree of polymerization. Okay. However, when you take the amplitude ratio, that is this Re over Rg, then L has gone, square root of n has gone, and this number is an experimentally measurable number, and it's independent of chemistry. So we will see later on, I don't think I will have time, but there is something called a Flory-Fox constant that has to do with 0 shear rate viscosity divided by the radius of gyration with appropriate units. That's a universal ratio which has a very famous value, and polymer solvent systems independent of the chemistry have been measured to have the same value predicted by theory. In fact, if you do not put in all the proper physics on a molecular scale, you will not get the experimentally measured value, and you, for instance, hydrodynamic interactions, if you do not put them in, you will get a wrong prediction of this universal amplitude ratio. And so it is a way of checking your theories if they are right, and so these numbers are important when it, because they do not, this number is just like a critical exponent, just like the half has importance, this number has importance, the ratio, because this is independent of any details. Have I done it wrong? It should be, oh yeah, of course, sorry. Well, we can do that. If that's the only mistake I've made, I've survived this.
That's okay.
Yeah. Yeah.
Sir, how exactly we define the persistence length?
Okay, so so we saw if you take this Li plus k dotted with Li, right, we derived this result, and this we saw this cos to the power of k theta could be written as e to the power of minus k over sp, or in fact e to the power of minus kl over lp. So what is this saying? I am looking at how is the bond Li plus k correlated with Li, and you see as the distance L or k between them grows larger and larger, their correlation decays. So in right, if you look at one bond and the next one, they are highly correlated because you have a rule that it can only make an angle theta, and so there's, you immediately will get Li plus 1 dotted with Li, you can find it, right. But as you go further and further away, and the idea is this persistence length Lp, and you can calculate it because we saw how Sp was defined as 1 over log cos theta, right, and so you know cos theta for your system, what is this Sp, and therefore what is Lp, and we know persistence length for, so DNA has a certain persistence length because it has a local rigidity. So for DNA we are interested in knowing how far along the backbone of DNA do you have to go before it becomes flexible, and so that's the idea, and that's okay.
So persistent length is the one where it gets uncorrelated.
Yeah, exactly, distance along, yeah. Yeah, okay.
Can you go back to the part where you calculate C infinity?
I calculate C infinity, was that after this, yeah?
So for a chain when theta equals 0, I would imagine that the end-to-end distance would be n square L square.
No, 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 when theta goes to 0, cos theta goes to 1.
So it never.
Exactly. So in this whole derivation, implicit is the idea that theta is not 0, because along the way you would have found you are dividing by 0 somewhere. So you have to say it can be a small number at best. Okay, yeah. Otherwise it's diverges. The nk. So we know a freely jointed chain, right, consists of a set of bonds that are connected together that are not correlated to each other, right. So this I am saying a Kuhn chain is nothing but a freely jointed chain, it's just bonds connected to each other, but I want to put a little more restriction on it, and I say it's a Kuhn chain that represents some other model, because I am saying as long as I retain the properties of that other polymer, then I am going to replace it with a freely jointed chain, some large scale properties. So I showed as an example, I took a freely rotating chain that has an Re squared and an L, right, a contour length and a end to end vector, and it is not a freely jointed chain, it is a more complicated model. I want to replace this with a freely jointed chain, okay, which I call a Kuhn chain, and I say how do I replace it in a consistent way? I will use a freely jointed chain that has the same end to end vector average value and the same contour length. And so what should my Bk and Nk be? Because I know if I travel along my freely rotating chain for a distance equal to the persistence length, it becomes uncorrelated. So what should my length of each bond in my Kuhn chain be such that each one is uncorrelated from the next? If it is supposed to represent a freely rotating chain, I know I have to go long enough along my freely rotating chain so that it is not correlated. Yeah, and we will see, we will even simplify further because we are only always interested in large scale properties. Sorry, I will answer.
So then what is the difference between Cohen length and persistence? Because Cohen length also, after Cohen length,
correct, that is it, you can actually show it is twice the persistence length, it is exactly twice the persistence length. Yeah, same. Yeah, sorry, no.
This whole derivation was followed by the assumption that it is a freely jointed chain, and that was also the reason, this led to the confirmation question, that was also the reason for the average of the product was equal to the product of the averages, right? So if I do not take the assumption, will this derivation be some limit to be applicable?
No, so you always have to, for any model which has local correlations, which is why you can't separate the averages, you need to coarse grain to a or go to a more coarse grained level where you can lump monomers to a point where they are not correlated. Yeah, but you can always do that if your chain is sufficiently long. Okay, good, great, thanks.